would like to thank to organizer to give me such a good chance to communicate with so many good researchers. So my talk today is about partitions in repartition theory and some connection with the integral systems. Uh, so my university is in Qingdao city, so it's a very beautiful city. So they have a nice beach, and so welcome to visit Qingdao and collaborate with us. So my talk will be separated into several four directions. Firstly, I would like to introduce the additional symmetries of integral systems. These additional symmetries can constitute a block type algebra or quantum torus algebras. And the second direction is from, as we know, so one single partition will correspond to a Schur function. Schur function will be a special top function of KP hierarchy. So there is another double index extension of Schur function. It's called universal character. This will correspond to a double partition. The third direction is about the refinement of partitions. It's called Lie diagrams in algebraic combinatorics. So this Lie diagram can be used to do a classification on KP solid graphs. The last part is about the duality of partitions. So Hessian system, it's a Hessian system solution is called the surface operator. So when we consider the rigid surface operator, usually people study the S-duality of the partitions. So every surface operator will correspond to a partition. So the S-duality of partition will become the interesting subject. So surface operator is the solution of Hessian system. So let's focus on the first direction. We are sure algebra. So the algebra, as we know, if a linear space set by three properties, one the linear property, the antisymmetric property, and the Jacobi identity. The famous infinite dimensional Lie algebra called Virchow algebra. It has just the one index. If we do a double index extension, so this will be called block algebra. So when we consider two non-commutative two torus, so UV, if you switch them, then you get a Q, quantum parameter Q. Then there is a quantum torus algebra like this. So when Q go to 1, it becomes the block algebra. So if we do a quantization using a normal order. So this operator will have a central extension. The KP hierarchy is a fundamental integrable model. So people usually use the pseudo difference operator. So from d 1's power to negative infinite power. So it has infinite time variables. This is called KP hierarchy. Here, Bn is L to nth power and do a non-negative projection to the D operator. So this KP hierarchy has a lot of applications in many fields. This Lux operator can have a dressing structure. This S is called a dressing operator. It's starting from 1 to it has an expansion around the infinity. So then the Lux equation will be equivalent to a dressing operator satisfy the Satu equation. So this S is operator, this operator, and also this operator. This is called the Satu equation. So all of Schumann's operator can be used to construct the additional symmetries. So all of now this all of joined our group now. All of Schumann operator M is like this. In the middle, it's a gamma operator. Then do a dressing transformation. You get all of a Schumann operator. Then we can get a canonical relation. Then we define the additional flows. Here we use M to M, L to N. Here we use exponential to some power and Q to NL using capital M and capital L. We can we can find that this is a W infinity algebra structure, and this is the quarter term torus algebra structure. These flows, we can find that they commute with the original KP hierarchy. That means they are symmetries. They are symmetries of KP hierarchy, but they don't commute with themselves. For example, this DTLK star flow, they have a torus algebra structure. This is the flow on the, for example, Lux operator or wave operator. But if we wanted to find a representation of top function space, then we need to use the definition of top function as this. Here, phi is the wave function. You have in the numerator, you have a shift of top function, then over top function. Here you have a plane partition, plane function or free function. People usually call this exponential of the free function. Then you take additional flows, TPS. We can find here, the right side, this is an operator acting on top, then over top. Here is a shift operator, then minus one. That means that if we ask this to be 0, then you can find the right part should be a 0. That means that after shift or without the shift, they are the same. That means this one will be constant. That means WSP plus 1 operator acting on tau is equals C tau. C is a constant. This is called a Weierstrass. It is called a W infinite constraint. It includes the famous Weierstrass constant. This constraint is used for in many fields like the string theory or the how to do reduction from KB hierarchy to Pauli equations. They also use this Weierstrass constraint. So it has many connections with other fields. And the top function can have a lot of interesting structure. If we focus on the polynomial solution of top function, that means sometimes people also call it a rational solution because later we will use the solution of KP equation U have a relation with this tau. Allowing tau take a second derivative, you will get the solution of KP equation. But if we only think about this tau, this is the rational polynomial solution. Polynomial solution for any partition lambda. So S lambda T, this is called the Schur function. Schur function is a tau function of KP hierarchy. If we do a linear combination of these Schur functions for different partitions, this coefficient should satisfy some constraint. This constraint will be called the Bloch relation. Yeah, so sometimes the people do a Milnor transformation. That means this T variable, T1, T2, T3, they have can be write infinite power sum or some trace or matrix. Then it will be have a connection with random matrix theory. So this is the first part. In this part, we did a lot of studies like for total system, we can construct the block algebraic symmetry and for the Sokolov hierarchy and some super integral system, we can find the super block algebra structure and the BC total and the super CKP. We can find the super Weierstrass structure behind these additional symmetries, and also some other different Li type, for the A type, B type, C type, and D type, and from a supersymmetric extension, we can construct the n equal 2 super block algebra structure behind these integrable systems. This is the first direction. The second direction is from single partition to double partition. As we know, this free function E2 cassette, if we do a expansion, then Hn is sure a polynomial. If you give one partition lambda, lambda 1, lambda 2, lambda L, so we can construct the Schur function. This is also called the Jacobi-Trudi formula. This Schur function will be a top function of KB hierarchy. The natural equation is we consider double partition. You have one partition lambda, another partition mu. We can construct a twisted Jacobi-Trudi. That means the first several rows is above the mu partition. The next several rows is above the lambda partition. And also, they depend on different time variable, different sequences of time variables x and y. So this is called the twisted Jacobi-Trudi formula. It's a homogeneous polynomial. It's a symmetric function. So a natural question is this kind of universal character polynomial satisfy what kind of integrable hierarchy? In 1804, so Chuda found a integrable hierarchy called the UC hierarchy. It's defined by the generalized vertex operator. So why we call it a generalized vertex operator? Here, usually in the vertex operator, we have annihilation function part. Another is generating creasing function part. Here, x we do a shift as a dy derivative operator, and also y function you do a shift with respect to x derivative. So this will be called the generalized vertex operator. Using this generalized vertex operator, you can ask them acting on the highest weight 1. We can get the universal character. So this will be a generalization of KB hierarchy. Here, this graph, this table shows the difference between KB hierarchy and the UC hierarchy. It's like a twisted gluing of two different KB hierarchies. So Sato-Grassmann becomes double Sato-Grassmann. Okay. Konkoff and someone else, they studied cylinder partition. Firstly, they started from the random partition for single partition, as this. And later, someone studied the plane partition. Plane partition is related to three-dimensional Young diagram. That means every slide here is a single partition. And this is cylinder partition. Cylinder partition means this is a sequence of partition 5, 1, 7, 2, and 4, 1, 2, 1. This is one sequence of partition. There's another sequence of partition 1, 2, 3, 1, and 1, 0. So you have two sequences of partition, and also you have an order, then have a boundary periodic condition. Then this will be called cylinder partition. From this cylinder partition, we can get a universal character. From this point, we studied some connections between UC with some quantum integrable hierarchy, like quantum integral system, like a phase model, quantum Gaussian model, and super quantum spin chains. The T-master operator of this quantum integral system will be related to the universal character. And also from different type of Lie algebra, from example B type and C type, and also from combinatorics like parasitic KP and BKP, these things we do some generalization. Also, we can study the Littlewood retardation rule of this universal character. And you see also can be connected with the Afan-Yangtze because three Young diagram is related to Afan-Yangtze. And also recently we collaborate with Mironov and Orlov using the universal character to connect with the hop of link. And also we studied the matrix models which correspond to the universal character. This is the second direction. The third direction is about solid graph or KP solutions. KP equation is like this. It's a 2 plus 1 dimensional integral equation. In the bracket, it's a KdV equation. So if we do a transformation as U equal second derivative law in tau, so this tau can have a very beautiful structure. It's a Wronski form. So inside every FR functions can satisfy linear heat hierarchy. So this linear PDE becomes very easier than the U if you consider the tau function structure. So now we only consider the exponential solution. Before we study the rational solution or U. That means the tau function is Schur function, polynomials. Here we focus on the exponential solution. So this is a fundamental solution of linear heat hierarchy. If we do a combination of these exponentials, this will be also a solution of the heat hierarchy. So every finite dimensional tau function will be described by this n by m matrix. So here we only consider the totally non-negative gross money. That means every n by n minor of this n by m matrix should be non-negative. Then we can take a law and take a second derivative. Otherwise, so the solution will become a singular. So every tau function will correspond to one point of finite gross money, totally non-negative. So if we draw the picture, you can find that so in the upper when y is quite positive, you have n solitons, capital N solitons. When y is quite negative, you have m minus n number of line solitons. So we can give every line soliton one ID. So every ID will correspond to a permutation group element of SM. So this this is called a solid graph. So every solid graph will correspond to one. This is called a chord graph, a chord diagram. So starting point is the pivot of the matrix. Then the down chord will starting from the non-negative. So every chord diagram can of course, so every chord diagram correspond to a permutation group element pi. So we can only see the asymptotic structure of this Grassmann NM solitons, but inside the interaction part, we cannot see it clearly from this chord diagram. That means the asymptotic soliton solutions will be one-to-one correspondence to chord diagram, but inside we can't see it clearly. So like this picture, so because the KP equation can describe the cellular water and oceanology, oceanic internal waves. So this is cellular water. So when Y is quite positive, we see three line solitons. when Y is quite negative, we say two line solitons. So this is so Y in the positive 3 soliton, negative 2 soliton. This is Grassmann 3, 5. Totally non-negative Grassmann 3, 5. This graph and this graph, they correspond to different time. So that means the different shift. It will shift next time. And the topology of this graph is quite simple because these lines cross at one point. But this one, you have a complicated topology. Like inside, you have one holes. So how to make a distinguish between these two graphs? We need to use the line diagram. Because the Young diagram without refinement can only describe the top cell of Grassmann. So if we wanted to see inside clearly, like this in the middle, big. So the one-to-one correspondence between line diagram and the solid graph was described by Kodama and Williams in Invention Math. How to describe the correspondence? That means for Young diagram, you don't have a ball, a white ball inside. Then you will draw a crossing line. That means you must go to the opposite side. If it's empty, that means you can only turn left, then turn right. So you draw this is called a pop dream. So every point will go to the tunnel according to these rules. Then we can find the Young diagram without the refinement can only describe the top cell of the Grassmann. If we wanted to see the smaller cells of the Grassmann, we need to add some white balls inside the Young diagrams. That means this will become the cross. Otherwise, it's turn right, turn left. So every this straight line will be pivot, 1, 2 pivot, 4 pivot, 7 pivot. Other side is non-pivot. So every number will find a point to go out. Then this 5 and the operator number 5 and 9, they will become one pair. So every pair will form line solitons. So this is 3, 5 soliton, so 1, 4 soliton, and in the middle. For different type of line diagrams, so the intersection part become different. A symptotic case can only the code diagram is enough. But for if we wanted to see the inside, the intersection part clearly, we need this line diagram. So every line diagram will correspond to a permutation group element of S. Here is S9. What we did recently is about the regular line solitons of Geffen decay hierarchy. For example, KDV, Bosnisk, any reduction of KP, we finished that. So we find the Bosnisk can only have one, at most one Y-type soliton. That means because this permutation this is three cyclic permutation. So every 3 cyclic permutation means one resonant soliton, Y-type. You have 3 lines. So here you have just one line. There's one soliton. So the one soliton. You combine this soliton together. The one important thing is this permutation a small group cannot interact cannot cross with another one, then we can keep the regular condition. For example, so every alpha you have corresponding to different curves. For KP, for KTV, it's elliptic so curve. So for Bosnisk, it's a cubic curve. So give every alpha you have one solidity or Y-type solidity. Give another alpha, you have another small group of ground mining. So we need to combine these ground mining together, then to get a big, totally non-negative ground mining to correspond to a more complicated land solidity. So we can find so Bosnisk can have at most one Y-type solidity, others just land solidities. We find a general rule for a regular land solidity or girlfriend decay. So how to get all the regular land solidity or girlfriend decay system? This is the procedure. So for every alpha, we can get for different alpha, we can find different curves. So every curve will correspond to a totally non-negative gross mining. So we combine this sub gross mining together, we get a big gross mining. This how to make this big gross mining be regular. The key is non-crossing. You combine this small sub totally non-negative gross mining. If we make them non-crossing, then the big gross mining will also be totally non-negative. Then we can so that means every big group of land solidities can be combined from fundamental subgroup of land solidities by combine them together. When you combine, you must keep this net crossing rules. This is the general classification of girlfriend decay system. And also we study the initial data problem of KP equation. For example, if we choose the initial data is a truncated land solidity, we just have one half solidity, no another half. And also we can study another kind of initial data is a V-type solidity. This is like two solidity, but we cut half, only keep one half. So this is a V-type land solidity. We can do a classification of this initial data problem. So with, for example, we fix amplitude and slope are two important elements of one solidity. If these two elements are fixed, that means this land solidity is fixed. Now we fix this amplitude of this land solidity and make this land solidity change. The amplitude change and this angle also change. That means this chord we fix and ask this chord to change, move. We can get a different kind of initial data. Then we study the evolution of this initial data. We find a general rule of this evolution related to the so-called chord dynamics. For example, this 3142 KP solidity, this initial data is a V-type. That means Y is very positive. We have 1,3 solidity. When Y is negative, we have a 2,4 solidity. So it will generate a 3,4 solidity and a 1,2 solidity. It should obey a minimal energy rule. But here we can find there is a very huge land solidity appear. This is called 1,4 solidity. From this chord diagram, we can't see this 1,4 solidity because it's in the intersection part. it's this for solidity is a asymptotic solidity. This rule is the numerical evolution. This rule, three pictures are the exact solutions of KP equation. So we can find that the error becomes smaller, go to 0. And at last, we find the general rule of this evolution for V-type solution obey called dynamics. Then so every the rule is like this: the upper chord, the left point should be fixed. The right corner, the right chord, but the downside chord, the right point should be fixed. Between two fixed point, maybe here. So the upper chord, the left point is a fixed point. The upper chord, the right point is fixed. Between two fixed point, it's a singular solution. It's a singular. So these 2 point, red point are singular. Singular means it will create a shock wave. It need to create one more solidity. From algebra geometry, this must create one higher genus. Other point are just free point. That means this point is a free point, where it will go to the nearest point. So at last, it will become the one solidity. And here, for example, this is a fixed point, this is fixed point. Otherwise, these 2 points are free point. Free point will go to the go to the point nearby. This point will go to the point nearby. That means there will be nothing. So this initial data, if we do a evolution, it will vanish. And for this special wave type solution, it will create a 1,4 solidity. 1,4 solidity means the gap is the biggest, the amplitude is the biggest. This will be called max stem. So people study the oceanology, they focus this max stem a lot because it's a huge wave, huge amplitude. It's sometimes called rogue wave in max stem. So we studied this evolution of different type of initial data. We find that it can be described our dynamics, our combinatorics subject called diagram. Also, recently we studied if we consider not only the totally non-negative gross money, if we consider some exponential, the minor become negative. That means plus negative minus, they will create a singular solution. That means this solution is regular, here becomes singular, then becomes regular when it go out. So how to do the classification of these singular solutions? We can find it. So the line diagram is not enough. We need to use a goal diagram. So what is a goal diagram? Because in line diagram, we only add the white ball. If we add a black ball inside the box, it will be called goal diagram. So this sometimes the solution is non-solid solution will create a singular solution. This is called solid collapse. So solid collapse should correspond to the goal diagram. So next, we will try to use the goal diagram to do classifications of solid collapse in KP line solidities. This is the third direction. The fourth direction is about the S-duality of ion diagrams. So as we know, if we combine electric and magnetic field together, it's unified to so-called gauge theory or Yami's theory. Usually to study Yami's theory, if we study the symmetry of this gauge theory, we usually use a Lie group to describe. People do study two kind of duality. One is S duality or the Lie group. Another is the T duality. But the T duality is not so interesting. S duality is more interesting. So S duality can map the Lie group to its Lagrange dual Lie group. Meantime, one parameter tau becomes 1 over tau. So that means one side, if tau is small, another side, 1 over tau will become big. One side is electric, another side is like magnetic, because electric is strong, magnetic is weak. So this duality people care a lot. So for different kind of Lie groups, this constant Ng will become different. Sometimes this tau is called a gauge coupling constant or string coupling constant. Sometimes using Planck constant, many kinds of names. Sometimes called the Zener expansion constant. Waiting and a lot of professors they studied N equal 4 super EMS theory a lot because it has the biggest supersymmetry. When they studied the two-dimensional defect of this N equal 4 super EMS theory, that means you have 4 coordinates. You just consider two of them. You find the solution of this two-dimensional case. That means it's called a surface. Why is it called a surface? Because we only focus on two-dimensional. Then we can get a Hessian equation. Hessian equation it's a one form gauge one form, another is a scalar one form. So you have a zero correct condition, and this star is a huge map, huge star operator. This Hessian equation, if we do a setting, so using coordinate transformation to r and theta, do a rotation invariant axis. That means here A, you don't have a dr part. Then to change r to log r, the s, we can get a Namo equation. Namo equation is integrable equation. It has many kinds of solution like elliptic solution, many kinds. But waiting, they care a lot about this rational solution. So S inverse. Here they plus a fluctuation constant f here. So when this Tx, Ty, Tz, they satisfy a representation of the SU2, A, B, C naturally satisfies the Namo equation. Then further go back, it satisfies the Hessian equation. So for different type of Lie groups, B, C, and D type, the difference is this region operator, they have different partitions. So every part is, for example, T plus NK is a NK dimensional irreducible representation of SU2. So if we do a complexization of A and phi, so do an integral, path integral, this monodromy will not depend on the contour because zero curvature condition. Then we can get U have monodromy U have this form. So T plus is a nilpotent, and this U will become the unipotent. So when people study the semi-simple case, so this U should multiply with element S case. There are some result about the nilpotent orbit. For B type case, the partition, the sum of partition should be odd, and even integers appear an even number of times. For other type of Lie groups, they have different constraint about this partition. So people, when they consider the physical background, they use a rigid rigid condition. What is rigid? That means this conjugate class is have the small have the smallest dimensional. It does not have a parameter. It's a non-perturbative conjugate class. It does not depend on any parameter. So from the partition, the rigid means for B and D case, no for any case there are no gaps, and also for B and D type, so no order integer appears exactly twice. For C type case, so no even integer appears exactly twice. This is called rigid partition. Rigid partition. Um, After adding rigid condition to these partitions, so for being case, the bottom row should have order boxes, then pairwise. So in every pairwise, the two rows should have the same parity of the number of the boxes. So when if the row number is even, that means the shortest length has to be even. For other type, D type and C type, they have other different constraint. When we consider the gauge semi-simple case, the periodic condition, because the rigid condition means that it does not depend on parameter. That means that the periodic condition becomes centralized, the commute. For S is 1 plus minus 1 minus 1 minus 1. Then we can find the B case will be separated into two parts. One is B type, another is D type. So D type will become the D type plus D type. C type will become the C type plus D type. So for some simple case, so we need to consider a double partition, a pair of partitions, lambda prime and lambda double prime for BCD case. When people study the invariant of S-duality of these surface operators, sometimes they study the dimensional. Gukov and Witten in 2010, they have one paper. The title of the paper is called "Rigid Surface Operator." Then Willett studied a lot about this rigid surface operator. The one invariant of this the S-duality is called dimension. Dimension is very simple, so it's not so interesting. Another is the discrete environment. This discrete environment for rigid surface operator, the left side is the center. The right part is the fundamental group. So one side is algebraic, another side is topological. So they have a dual from the S-duality map. By the way, most of people they focus on two other different environment. One is fingerprint, another is symbol. Fingerprint was constructed from the characteristic map, and the symbol is based on the spring correspondence. So there's a conjecture. These two environments should be equivalent, but no one proves that. Recently, we finished the proof of the equivalence between these two environments. So let's focus on the definition of this environment for symbol. What is symbol? For example, for Bn case, you have a partition lambda. For lambda, every lambda k, you plus L minus k. L is the length of this partition. So you get a sequence of numbers. This sequence of numbers, you take odd part left out and even part f left out. You get f and g sequences. Using f and g, you get alpha and beta, two sequences of alpha and beta. This is called the symbol environment of the partition. In 2024, in our CMP paper, we give a very simple, much simpler computation for the symbol of one partition. When t equal -1, it's B type. When t equal 0, it's C. T equal 1, it's D type. So for different type of Lie group, the ith row, we calculate the length of these numbers. We can find the contribution of every row. We combine, we do a sum of the contributions of every row. We get the symbol of the whole partition. So this calculation is much simpler, much simplified by us. So, for example, this is a S map from B type to C type. And you can find this map preserves symbol environment. Left side, you calculate the symbol. Right side, you calculate the symbol. They are the same. Symbol is the environment of this map. And for general theory, so S can map for a Lie group, they have a double partition. You map to the double partition of its Lagrange dual group. So, for example, this as for unipotent case is the one partition becomes empty. So this map maps B to C type partition, rigid substrate partition. We can find in some, for example, this is the B6, this is C6. Some partition you can't find its dual. Some duality of partitions are missing. For B4 and C4, we can find this mismatch problem. And we do a classification of these problematic surface operators. Why they don't have the duality? In what conditions they don't have the duality? Sometimes because the rigid condition 1, sometimes because the rigid condition 2. We do a detailed classification of these problems. We construct many algorithms to all order BN and CN. For any N, we do a classification. And another environment is called fingerprint environment. It's quite complicated. For example, you have a double partition. You do a sum, you get a whole single partition. We construct a new partition. This new partition mu almost the same with this original partition lambda. Sometimes the only difference is sometimes you need a +1 or -1. That means sometimes you need to delete one box. Sometimes you need to append one box. And from this mu, we can construct a function tau. When some mu r equal m, and at least one condition of these three is satisfied, then this tau function will become 1. Otherwise, it will be -1. Otherwise, it's 1. So for tau equal 1, you have two same columns, just keep 1. For tau equal -1, you have a column, you cut half, just keep half. So you will get a sequence of two natural numbers, alpha and beta. This is called the fingerprint environment. So this is much more complicated than the symbol environment. Then I will tell you, you don't need to calculate the fingerprint anymore. You can, they are equivalent. The symbol environment is equivalent to the fingerprint environment. So this is a conjecture we proved and finished. We spent a lot of time to prove this conjecture until the last year we finished the proof. Uh, and recently we have some new progress. We proved symbol is equivalent to the fingerprint environment. Now we can construct from one environment to another one. And also we found a powerful probe. We call it a heat environment. This environment is very useful to test whether two rigid surface operator is dual or not. And also, this probe can identify dual pairs of rigid surface operators that share the same fingerprint and symbol environment. We can make the distinguish between these two to make a classification of the rigid surface operator. And another new progress is because of the rigid condition, some surfaces, for some surfaces or surface operators, we can't find its duality. But we can expand the scope of rigid surface operator. We can relax the condition. Don't put a so restricted condition. We can find they are dual. We propose a directly natural and precise dual map. This map is very powerful. It can address some issues, including weighting issues. Witten found some rigid surface operator. He found the duality of this rigid surface operator is not exactly the one founded by Lustig. In our construct of the SDO map, we solved these issues and other partial problems clearly. So I think this is the end of my talk. Thank you.
Okay. Let's thanks